just pulling by axial stress X. Okay, you are pulling by axial stress Y. Okay, so this is a case of plane stress membrane. Okay, so when we say plane stress, means that there are no stress in the Z direction. Okay, so this is what we call plane stress direction. 所以我们刚之前所学的一根杆还是什么 ？OK， 你去拉它，它的这个应变就跟它应力的方向一样。但是你在平面制动的时候，你的是活活，你在拉力的方向，垂直力这个拉力的方向，你还有一个横向的应变。In this case, how do we find the stress relationship? Okay, so it's difficult to do the summing of the stresses. So what we did is doing the summing of the strain. So it would be coming from direct stress. It could coming from the quantum ratio effect. Because in the case of zero thickness direction stress, so you are able to do the sum. Okay, so let's come to that. So we have written the strain in the x direction, coming from direct stress, coming from indirect stress. Likewise, the strain in the y direction. And shear stress altogether, shear strain altogether you have two strain in the x direction, y direction, shear strain. They can be expressed in terms of stress in the x direction, y direction, and the shear stress. And now you would like to find stress versus the strain. Okay, so in this case, so you are doing the transpose. Okay, so now rather than stress, you want to find the strain relationship. Okay. So this is the stress-strain relationship. You know why we need that? We need that because you later going to calculate the stress. Okay. So the way to do that is doing the inverse. How do you do the inverse of stress relationship? To do the inverse, you apply your Cranmer's rule. Your Cranmer's rule will just apply to two unknown variables. It will also apply to three unknown variables. Okay, except now the determinant in the numerator got to have the first column replaced by the strain. Okay, so this is the Cranmer's rule. 同学，你如果线性代数的这个Cranmer's rule不清楚，你要回去查找一下，因为实际上这个是解联立方程组最简便的方法。所以用行列式 ，OK， 两个行列式，分母的行列式基本上是所谓这个系统矩阵。OK， 分子的行列式是系统矩阵的比例，是长是打还是列？都或者长是弱，列，你是把列利用优属项的力来取代。OK， 所以that way， 是吧？你讲错吗？OK，yeah, correct。所以是长列打过来。OK， 讲中文打过来，不叫列行式了。OK， 列 OK。好，所以我们是做一行。Okay, that way, anyway, we managed to solve for the unknown stresses. And these unknown stresses cannot be re-expressed as a matrix times the strength. Because this is a 2D case. So these matrices is what we call your consecutive equations. Okay? They will give you the stress. Okay? Take for example, the stress in the x direction. 你看这个你的 x 方向的应变，我们来看一下，单向来写。The x 方向的应变。What is the stress in the x direction? The stress in the x direction is E over 1 minus Poisson ratio squared times the strength x plus Poisson ratio modulus divided by 1 minus v squared times E1. OK， 看到没有？你现在这个情况底下，怎么认知呢？你的应力，它是 x 方向的应力是 x 方向应变乘上一个数，再加上 y 方向的应变乘上一个数，所以这个时候告诉你，你的应力它是一个两个方向的应变耦合，不单纯是一个方向。So in this case, we know that the stress is a result of the couple effect from the strain in the x direction and y direction. Likewise, you can write the same for the stress in the y direction. There's also a couple of strain effect in the x direction and y direction. The only one independent is the shear stress. Shear stress is only depending on the shear strength. Okay? So they are simply calculated. Okay? So geometrical wise, so what are the deformation gradients that is encountered? One is elongation in the x direction. The other is elongation in the y direction. This elongation can be expressed as the chain of displacement between the two ends. And that is an elongation. And how about the strain? The strain is then the displacement difference between the two ends divided by the initial length. 所以你的这个一根杆你去拉长它 ，OK， 然后你两端的位移差就是你长度差，长度差再除以圆长，就是你的应变。然后刚才算完横向的应变，你还可以纵向的应变，你的垂直方向的应变，它很可能就是上端的位移，你的下端的位移，再除以圆高度 ，OK， 所以这个是两个方向。然后还有另外一个就是它若干比率，这个上方的位移等于下方的位移，那就看比率，或者左边位移等于右边位移。然后剪切形变的这个有几种，一个是随平方向的剪切，全方向剪切，再来一个是任意方向的剪切，基本上是一个方形，它的夹角被扭曲 ，OK， 然后就变成从一个方形变成一个菱形。所以总的来说，虽然跟你们讲了这么多应变，但实际上应变的表示方式可以写成是那个位移场变化相对它的原尺寸变化。So in this case is a summary of the definition of strain, which is defined as deformation gradient. It's the elongation chain with respect to the initial horizontal length. This will then be the strain in the x direction. And then the strain in the y direction will then be the vertical height chain divided by the initial height. And then this shear strength is more complex. Is then del u del y. That is the angular chain. So if your top left corner is moving horizontally with respect to the height, then you have the strain in this direction. And then next, at the bottom end, if it's undergoing the shear strain, there will be a height rise over the initially horizontal length. OK， 好，然后我们接下来看一下，接下来我们来要分析的是你的薄膜元素的力。 have learned about the truss element. Are we going to apply it the same to this plane membrane element? Yes, we can do that. First thing we do is first get the constitutive equations, the stress-strain relationship. We then pre-multiply with this D matrix. This D matrix is your constitutive equation. Okay? And then what about the energy? Okay, the energy we can go step by step. Okay? 好，我们就再重复一下这个元素的这个定义。You learn about the rod. It's very easy to write the. Okay. So this is subjected to F1, F2. They undergo U1, U2 displacement. The total energy you have is, okay, your stress strain, and then integrate with volume minus F1 U1 minus F2 U2. That's for the rock element. Okay, what is your stress strain? Your stress is your force. So you can express this as your modulus times the strain and then dV. Okay. So divided by 2, 1. So this one, and then the epsilon is U2 minus U1 divided by 2. Okay? So if you're now going to find your force F1, then you're going to find the energy del U1. Okay? Then this one will then be equal to 2E epsilon divided by 2. And del U1 will then be left with minus 1 over L, and then the dV is then your A dx. Okay, minus, okay, minus your F1 1. Okay, so this one is minimum energy case. Okay. In this case, you write your F1 is equal to your what we call your this your strain. Okay. Okay. This one is del U del X times 1 over N A dx. And what is your U? Your U is your N1 U1 plus N2 U2. And then the U del X is then del N1 del X U1 plus del N2 del X U2. Okay? So you go through that. If you go through this, then you're going to have F1 equal to, this one is actually, if I express it fully, what this is my del N1 del X. So this, when I expand this out, is then going to be EA, and then your del N1 del X squared plus del N1 del X del N2 del X dx. Okay? But you have to multiply this to be U1, and this is U2 dx. So in this way, you obtain this dA integral of del F1 del X squared del N2 So this is just to give you a revision how potential energy method was built. Okay? So what I do is, this is for simple rock. Okay? So the breakthrough of the invention of finite element starts from this potential energy approach. But how do you jump from a rock to a 2D plane? Okay? From the rock to the 2D plane, the difference comes from the constitutive equation. Okay, we're going to replace one by one. So for the 2D plane, at the time of this invention, I think it's the scientist from Washington University and engineer working with Boeing. They still call it plane. Okay? But this is no more the plane we define. Okay, this is actually the membrane. Plate is subjected to bending. Here, this is a plane stress membrane. Okay? If you're going to write epsilon x, epsilon y, and then the tau, okay? You're going to multiply with the matrix, what we call D matrix. It's related to the strain in the x and y direction as well as the shear strain. Okay? So now, if you're going to apply this approach, I'm going to replace this exactly the same. My potential energy, I can write the same. Okay? But this time round, the stress will be stressed in the, let's say, not 1. Okay? Not 2, not 3, not 4. Then you have the F1x, F1y, F2x, F2y, F3x, F3y, F4x, and F4y. Okay? So my total potential energy will then be my stress, strain, product, and the volume minus F1x and U1 minus F1y and B1 minus F2x U2 minus F2y B2 minus F3x U3 minus F3y B3 minus F4x U4 minus F4y B4。OK， 所以同学看到吗？我现在如果要用刚才应用到反单元数的方法去算你的总势能 ，OK？ 然后对于一个平面元素，因为你4个节点，4个节点上各自有4个节点上的力，然后4个节点各自有4个节点上的 x 方向的位移，所以你对外做的功 work done， 你可以直接的这么写 ，OK？ 对同学而言比较难的现在是，这个应变我们要怎么解决呢？我们来写一下。How do you analyze the strain? Because the complicated thing is your strain energy. Because I know about my 1D strain energy. How do you jump it into your 2D strain energy? Let's see. how to define your strain energy? So if you want to define it, okay, you can say my strain energy. Let's tackle this expression first. Can be expressed as, what do you express? This is a stress expression. Okay. Okay, this is 3 by 3. This is 3 by 1. Okay. It's difficult to express it. How do you get this as a 1 by 1 matrix? Okay. The only way to do that is doing the transpose of that. When you do the transpose of that, this one will become the matrix transpose. You have to solve. 你们会算那个两个向量相乘，然后去 transpose ，OK， transpose 过后变成 B 乘 A。Okay. This is now my stress. How about my strain? My strain is simple. My strain is epsilon x, epsilon y, and the shear stress. So this now become transpose will then become epsilon x, epsilon y, gamma, and then my E matrix transpose 3 by 3, and then my epsilon x, epsilon y, gamma 3 by 1. This is 1 by 3, 3 by 1, and 3 by 3, 3 by 1. So if you're not sure, what do we do? Let's substitute in your E matrix. Okay, your D matrix is, okay, if you're not sure, D matrix, I write it one more time. The D matrix is E over 1 minus B squared times 1 minus B, 1B, B1, 0, 0, 0, 0, and then this one is 1 minus B2. Okay, when you do the transpose, what does it change? Transpose means row becomes a column. Okay? And then last one. So after doing the transpose, it remains the same. Because the D matrix is symmetric. 所以你的这个本波方程这个相当于你的 E 在平面上，它是一个这个斜边上对称的一个矩阵，虽然它被转置过后 ，OK， 它维持原样 ，OK， so now you have epsilon x, epsilon y, gamma, okay. Let's expand that out. So row matrix re-multiplied with column. So then you have the first one becoming epsilon x plus b epsilon y and then 0. Okay, this is your first one. Okay. And then next is your row matrix and the second column. Then this is your epsilon b epsilon x plus epsilon y plus 0. Then the last one will then be my row matrix and the third column. So this is your 1 minus b over 2 gamma. OK， 好，我们处理完前面这两项 ，OK， 我们再抄一次，抄一下。 multiplication, what would I have? I will have epsilon x squared plus b epsilon x epsilon y plus b epsilon x epsilon y plus epsilon y squared. Okay? And then plus the gamma term. What are the gamma terms? We got a number of gamma terms. This one is epsilon x plus b epsilon y plus b epsilon x, and then plus 1 minus b squared gamma. All these together multiplied with the gamma. Okay? So you can see that if we're going to express the strain energy, okay, the expression is going to be very tedious. Okay? So why there is an invention of matrix method is I don't want to handle this tedious stuff. Later I still need to do the differentiation. 所以二维的这个应变呢，你要去做展开，已经很复杂了。OK， 所以我们之后要去做推导的时候，我并不寄望我还要做这种展开式，然后再去做微分。OK， 比较好的方式是什么呢？我直接去保留它的矩阵形式，然后在矩阵上做微分，做乘除，做相乘。OK， so this is just to give you a flavor of it. How tedious is it? It's not complicated. It's just simply tedious. Okay, so now we come back to our matrix method. OK， 之前之所以把这个矩阵重新写一次，就是给你有一个感觉，那个矩阵是什么。So the reason why we write this is to just give you a feeling what this matrix is. So our expression for potential energy is then half the stress transpose times the strain. But I now express my stress as a transpose of strain vector, a constitutive equation times the strain vector, and then minus the external work done. Okay? So now, okay, let's express everything in terms of the vector or matrix. If now I would like to have partial differentiation of the total potential energy with respect to U1, I can do two things. First, I differentiate my E. Okay? So let's come back and see what is my strain. 好，我们的应变。You can recall your strain vector. Okay? This can be expressed as epsilon x epsilon y and gamma. And my epsilon x is differentiation of my displacement. Is then this n1 u1 plus n2 u2. Okay? So here you see the strain is independent. The displacement is independent. Okay? In a way when you define. Okay? And then your gamma is del u, del y, plus del b, del x. So that is then my here. So we now relate the strain to displacement gradient. 这是给大家一个脑子一个回顾。你的应变实际上是你位移对空间上的微分，在 x 方向的应变，在 y 方向的应变，还有剪切应变。所以你 x 方向的位移对 x 方向的空间微分，就是 x 方向的应变。你 y 方向的位移对 y 方向的高度微分，那就是 y 方向的应变。然后你的剪切应变，那就有点复杂。横向的位移对高度微分，垂直方向的位移对横向长度微分，你就得到了剪切应变。OK， 你如果对这个定义比较深入，你最好是看前面的图。So now we revise how your strain is defined. The strain in the x direction is displacement gradient in the gradient of horizontal displacement with respect to horizontal length. The strain in the y direction is the differentiation of the vertical displacement with respect to vertical coordinate. And then the shear strain is more complex. You differentiate the horizontal displacement with respect to the height. Plus, you differentiate the vertical displacement with respect to the horizontal length. Okay? So now, we have the expression of the energy in terms of strain, in terms of forces, pre-multiplied with displacement. Okay, but you have to realize that your strain is a function of displacement which was defined here. Okay? If now I want to find out what is the force on knot 1, U1, okay? I then got to differentiate the energy with respect to U1. Then I will have F1 X, okay? But then you got to differentiate the potential energy. Okay? How to differentiate that? 我们来对这个应变的做微分。But now we handle the expression of the strain energy in the vector form and matrix product. OK， 还有这里你的体积的积分，现在你要写成厚度乘上面积。OK， 跟以前的微分方式不一样，以前是截面积乘上长度。So previously you are doing the integration of a dx. Okay, but now you are doing the integration of t dA. Okay. And then now let's do the differentiation. Okay, the differentiations. Okay, after you have gone through this, if you do the differentiation of the strain energy, first differentiate with respect to U1. Okay, in that case, if you do that differentiation, okay, then you have half. I can differentiate del E del U1 D and F1 E, and then plus E transpose D del E del U1. Okay? And then this one will be A. They look different. But you know that this is a scalar， 所以这两个项啊，刚好是这个向量矩阵向量相乘，它的顺序微分的顺序刚好相反，但是这个是存量，所以一的转动等于一嘛，对不对？存量无所谓，所以这个时候你可以把它合起来，合起来写就是变成1/2两倍。 让那个 transpose d del e del u1 dA. Okay. So in that way, so you see, when differentiating these expressions, there was a half is right, but after differentiation, there is no half because it's double. I can write the strain differentiation at the front times d times e. I can also write it at the back. Okay? So what is the differentiation of the strain with respect to u1? So let's have a look. What is this del e del u1? Del e del u1 means that this del u1 is equal to 1. This del u2 is 0. Okay? 这是微分的过程就这么搞定。然后这个呢 ，What is del ey del u1? Okay? They are all 0. Okay? What about del gamma del u1? Okay? This is the only one left. The other are 0. 所以你对你的应变向量微分，对什么微分？对 u1，OK， 你结果得到的是什么？你得到的是一个简化的。Let me do the expansion to give you the feeling what it is. So we have to do the differentiation there. Let's try to work it out. So to give you a feeling. Okay. Okay, so you see, I now have my gradient. So what do I have? My differentiation of this expression okay, can now be expressed as this expression. Okay, or I can follow the not one. Okay. So these expressions can now be expressed as this is what? This is my del n1 del x times 1. Okay? And then 0. And then this one is my del n2 del
n1 del x u1 plus del n2 del x u2, and then your n1 del x v1 plus del n2 del x v2, and then this one is del n1 del x, and then v1 plus del n2 del x v2 plus del n1 del y v1 plus del n2 del y v2. Okay.
So you can see that, and then all together integrate with respect to the area.
So now you can do the expansion if you like. Okay? But if you don't like to do the expansion, please express them in the matrix form. Okay? I don't want to do any expression anymore. You know the expression is going to be very complex. Okay? Okay? If I don't want to do the expansion, what am I going to do? I'm going to write them in the matrix form for the last vector. How am I going to write this last vector? Okay? To write them, I pre-multiply u1 v1, u2 v2, u3 v3, u4 v4. Okay? You got it? And then this is 8 by 1 matrix, 8 by 1 vector. And then this one is going to what? Sorry, this is so it's depending on the number of nodes, okay? Then we're going to do that change, okay? So this one you're going to do the filling up, okay? Del n1 del x, and then this one is v1. So you're going to do this, okay? But before we have decided to do the expansions, okay, this tells you the framework. Later, depending on the number of the nodes you are handling, if you are talking about 1, 2, 3, 4, then this one has 6 nodes. Okay? But if you are talking about 1, 2, 3, sorry, if you are talking about 4 nodes, then you have F freedom, F degree of freedom. If you are talking about 3 nodes, then you have 6 degree of freedom. So, 这个暂时不展开。So we don't expand it yet. Okay, by doing this, okay, we tell you the meanings of the strength gradient with respect to U1. Okay, and the next important thing here is, okay, rather than using 4 node elements, I'm now teaching you 3 node elements. So this is what is called constant strength element. In the case of constant strength element, you have 3 nodes. So on each element, then you have U1, V1, U2, V2, U3, V3. Okay? And according to our previous idea about interpolation functions, if you are using linear interpolation or whatever interpolation, you can write n1, u1, n2, u2, n3, u3. What would be the interpolation function for? You make local node to have a shape function of 1, but opposite node to have a shape function of 0. So for n1, for node 1, the n1 is 1 at local point, but n1 is going to be 0 at opposite node. Likewise, for shape function 2, it's going to be 1 at node 2, but going to be 0 at node 1 and 3. And for shape function 3, it's going to be 1 at node 3, but it's going to be 0 at node 2 and 1. Okay, so that's the idea of shape function. Given that definition, you can then do the expansion like that. And then later you can do the differentiation of strain. In the x direction is del u del x. Then there's going to be del n1 del x times u1. 0 contribution from v2. And then next del n2 del x times u2. 0 contribution from v2. And then next del n3 del x u3. And then 0 contribution from v3. Okay? So in that way, you find out the strain in the x direction, and you also doing the same to find out the strain in the y direction. In that case, you have contribution from v1 times del n1 del y1 and del y. You have contribution from v2 times del n2 del y. You have contribution from v3 times del n3 del y. They're going to have 0 contribution from u1, u2, u3 to the vertical strain. Okay? And then the last row is the shear strength. This shear strength is obtained from del u del y plus del v del x. So each degree of freedom of displacement will have contributions. But you can go and do the figuration. Okay, finally, you see. Now I have my strain in terms of my displacement. Pre-multiply by the gradient of shape function, and that gradient of shape function is following the definition of the displacement gradient. Okay? And next, what about del Ex del U1? So if you find out, you will see that shape function gradient is independent of nodal displacement. The only thing that is depending on the nodal displacement is this displacement vector. So if you now take the gradient of the displacement vector with respect to U1, then you're only left with the first term being 1 and the rest being 0. 好，我们现在来讲一下你的应变向量。你的应变向量可以跟这个3个方向，这个2个方向的位移相关联。中间的这个常数项，基本上是形状函数对空间场上的微分。OK， 然后现在你的应变对某个方向位移的微分，它不影响你的形状函数在空间场的微分项，它直接影响的是你的位移向量。仅有一个 U1 对 U1 微分非零，其他项都零。Okay, in that way, you now got the partial derivative of the strain vector, and you now bring it to this force displacement relationship. Okay, it's quite a complex expression, tedious but doable. So just now you can see that what is this shape function gradient? 1, 2, 3, 4, 5, 6. It is 6 by 3 matrix multiplied with 6 by 1 displacement vector. Okay? 3 multiplied by 3 by 3. Okay? Let's write the size so that you have an idea. if you're not familiar with the matrix, yeah, this is to help you out. The size here is 3 by 3. And the first term is the gradient of your is a transpose of the shape function gradient. And then the first term is your one by 6. Okay, so what is your size of the box? Okay, it's 1 by 6 times 6 by 3 and times 3 by 3 times 3 by 6 and then 6 by 1. So after all this handling, you have only the scalar force. Okay, 所以你们要做这个计算，最好是用 Method。So Method is very good for this manipulation. You know what is Method? What's the full name of Method?
Mathworks，
猜到了没有 ？Method
那个什么 Mathworks，他说是 Mathworks。
Matrix Laboratory Method。OK。所以你如果不要花钱，还会有一个 Finite。Okay, Method is very expensive if you want to use it outside university. So that's why if you want to go for open source, then use Finite coming from France. Okay. So of course today you also can use Python because this matrix handling thing. Okay. So when you are going to handle such a thing, sorry, I'm not calculator. Okay. If I set the question for you to handle this, beyond your capability. Okay? So for this part, we just understand the derivation. We're going to use the final expression rather than drill you on the derivation. Okay? So, but before I proceed, you see here, the very important concept here is you need the gradient of shape function so that you can relate strength to displacement. At the same time, you also find the gradient of shape functions. It's important to find out your stiffness metric. This gradient of shape function, we denote this as B matrix. B matrix transpose times the D matrix times B matrix, and then times thickness and area will then give you the stiffness metric. Okay? Before we go derive the fit, so let's have some basic concept about the shape function. Okay? So given a 2D space, you now have the right angle triangle with not 1 at the origin, not 2 on the x-axis, and not 3 on the y-axis. How do you find the shape function? Based on our previous conceptual understanding. 所以我们什么也不推，我们现在去看看什么叫形状函数。形状函数根据我们之前的定义，它在那个节点上它要1，它在对面的节点要0。OK？ 所以它，你可以把它想象成是一个等高线 ，OK， 在节点 B 是1，在对面的线上是0。请问你的等高线的方程式怎么写？ So my first question to ask you, I have not 1 at the origin. Can one of you tell me what is the shape function in terms of x, y coordinate? 我现在节点一的形状函数，它基本上是一个等高线，在对边是0，在我这一个点是1。OK， 能不能马上讲答案 ？N1, what is N1 from my description? Okay. So this require your high school mathematics. 怎么定义一条线 So this is just basic concept. How do you find out the shape function for node 1? That shape function defines the iso line. Iso line means that the line of the height gradient. So here, even without any complex analysis, okay, if I now have point 1, this is point 2, and then this is point 3 with a 0b. In the 3D view, you should know that this defines height of 1, and this defines the height of 0. So this is your N1. Okay. So what is your N1? Your N1 is 0 on the opposite node. 这看到没有？你的形状函数 N1 等于1在节点1 ，N1 等于0在节点2、3。所以现在你知道这条线怎么写了吗？So the shape function here is x over a plus y over b equal to, is it equal to 0 or equal to 1? Yes. Yeah, it's equal to 1. Okay. So you can now re-express my shape function N1 here is 1 minus x over a, 1 minus y over b， 对不对？所以你把节点带进来 ，a 0，哎，是不是正不对呀？因为它是1，所以我还需要减掉1，是吗？哎，这是对的。OK， 我们把0点带进来。OK， 啊，应该是对的。所以你 substitute 0 0 x y 0 0 into the equation here. I have N1 being 1. If I substitute 0, x is equal to a, y is equal to 0, then N1 is equal to 1 minus 1 minus 0. Okay? And then next, if I substitute 0b, then it's going to be 1 minus 0 minus 1. Okay? So that is a very quick way of finding the shape function. No, it must be a function of x and y. Okay. So that you have the iso line. Okay, being a linear with a linear gradient. Okay, after you have find the shape function for N1, would you be able to find out the shape function for N2? So N2, if I draw that, this is point not 2, not 1. So this is the opposite line, which is 0. So your opposite line is what? This is your x equal to 0. Okay? So what is my shape function? Is my shape function? It must be what can it be? It must be x over b. Okay? When I'm located at point B, I have the value of b over b. So this is 1. But if I'm located at point 1, so this is located at 0, 0. Point 3, 0, 0, A, sorry. 0, B. Okay, sorry. This has to be A. 所以你看，第二个形状还是找到了。OK， 是你对边设一个那个相似。OK， and now how about the shape function for N3? The shape function for N3 is then, if I'm viewing from this side, okay, this is my not 3, N3, 1. So viewing from this side, my opposite side is this. So this is y equal to 0. At this point, so my shape function is 1, then it must be y over b. Okay? 所以现在我们是单纯从线性代数还有这个画图来找出形状函数。Okay? Opposite line. Opposite line. The equation is opposite line, but it's going to be 1 at my local point. Okay. So what you see here, so this is how we define the shape function for geometry. Okay, but of course later we're going to show you we can derive it completely by algebra. Okay, but this is a quick one of having a grasp on the concept of the shape function. Okay? So how to handle any arbitrary triangle? Okay? So probably we shall have a break for 10 minutes. We'll come back again. Yeah, because the mathematics later will be more important. 好，我们先休息一下10分钟。OK， 等下才回来继续对谈。OK，that's it. OK， 我刚才给你10 minutes time。
因为这种就是一个方阵，跟一个1333的方阵，跟一个对面 M 接出来是一个1333，然后你要应用这两个，然后你要解位，今天做一半的结果，这个第一点今天上，这完全是方阵，完全是哦，对，这 KPI 这些东西也要说，有个指令叫 XYX， 你要跟他说我有这个东西。我就是变数，对，你要跟他说我有EILX， 它一说话是这样，然后这个东西可以拿来做对啊，他刚才讲过这个，用拍子，他可以拍子写，用拍子，就是你们会用拍子写，他会啊，我没有。没有啦，是那个把那个自己把那个做好，然后提笔上，让别人看到自己算的。
让我完全对老师想香水，很奇怪的香水。这样我受不了太了的味道，这很受不了的味道，因为还要烟味。他们敲开，
烟味一定是我不抽烟的。你要下课了？
你要看啊？
有没有啊？我不是那种人，而且其实来的人很少啊，少超多的。对啊，大家一定期中考都考不错。
期中考没过，还没讲完期中考，
期中考怎样？
好像还没讲分数啊。
有啦，上礼拜发考卷啊。你应该蛮高，因为他是照分数的，很快就念到你了。他上礼拜有发考卷？有啊。
在课尾不是？
你们上礼拜不是你的？他上礼拜下课的时候，
下课都发了。
那考卷在哪里？应该在他办公室啊。所以我很后面没念到啊。我不知道哎，因为我不知道你的名字是什么，但你们应该差不多啊。
所以我现在完全不知道我考多少。
我不知道我考多少。你要去他办公室问他，跟他说想要拿考卷。所以我再去吗？现在去吗？你要分析吗？就是类似他那个审判书报可以拿来做一个东西，是数列页转换或那个什么打乱转换，它甚至可以逆转换。对，你不知道不是可以。比如说你的 x 等于，看看是哪一个？他不用，跟特别人说，不是，我只想看他那个公式。
我还讲明天谈经济学，所以发现公式做出来考的怎么样？
哎，别说了啦，你跟他讲。你说那个叫什么 SYM。应该这样。哎呀，英文是怎么那你要先指定说你有个变数叫 S， 你要先指定。你有指定它的变数。
Okay.